Is that better?
Yeah, maybe.
Okay. My name is Kirk Wendell. In Dr. Bokel's absence, he said I could read this presentation to you. No, I'm just joking. All right. Whew, right? Hopefully. So I'm Kirk Wendell. I have been at Johns Inc. for going on 11 years now, and been starting to teach a little bit there. So Chuck asked me if I would sub in for him today, and we're going to talk about general pollution emissions. I'm a chemical engineer, graduated in 2006 from the University of Utah, just with a bachelor's, but that was enough to get a job, so I was gone. And 11 years later, still working, so that's good. All right, so general pollution emissions. Who read chapter 14 of the handbook as part of the preparation for the class? Man, nobody? Not even a little bit of it? I guess I get to eat all these candy bars. I was studying it while I was reading it to get ready for this class. I didn't want you guys to ask me any questions I didn't know. So I read through. I found a couple typos in there. I was going to give you guys a candy bar if you found them, but I guess I'll keep it for myself. Help with my boyish figure. All right. So today we're going to talk about different types of pollution, mainly ones that come from combustion process, how that affects the environment and humans, what we're interested in. We'll discuss some of the regulations that have been brought up to help decrease pollution, since it has effects on our environment, and how we can address that through the combustion process. So we're going to start with pollution problems. So it's day one of your JOB. That's not a text thing, it's an actual spelling of a word, job. Your boss comes up to you and says, all right, we have in our primary steam methane reformer, we're going to make ammonia. And the burners in our heater have been guaranteed by our burner vendor for certain emissions. And we need to go to our state and get a permit to be able to fire our heater with those emissions. So we list it out for you. You have 120 arch burners. It's a big, huge box. They're all firing down. They fire at 5 million each, and they've been guaranteed to not produce more than 45 ppm of NOx. There's 10 tunnel burners at the bottom of the heater, and they fire 10 million each. You guys jotting this down? There's lots of equations coming up. I'm just joking. They fire at 60 ppm each. Less than. 20 crossover burners. Okay, so as the heat from the burners goes into the heater, it goes into the process. We start cooling down the flue gas. We need to heat it back up. So we have the crossover burners to heat that back up. It's 20 of them, 5 million BTUs per hour each. And they're guaranteed no more than 30 ppm NOx. And then to start up the plant, they have 5 auxiliary boiler burners. Now these boilers, they don't fire all the time. Once we get the process going, they can idle those back a little bit. But they're designed for 40 million BTUs per hour, and they have a guarantee of 50 ppm of NOx. So, did you guys do all your calculations? What should we request from the state? They're probably going to ask for a not to exceed at a moment guarantee and a yearly exceedance. Okay. Each state's different. We get requests from all over the world. Each one's different. It can be a pain. It can be easy, depending on what the requirement is. So that might be something that you run into later in life, just as an example of what we're going to be discussing today. So here in this wonderful graphic, which doesn't show up as pretty as the colors should be. The sun is not green. The sun should be yellow.
Decontaminated.
Yeah. You're looking through smog. Whoops. Get my laser button right. Oh. So my blocking it with my finger? Anyways, I'll just use my finger. Smog is causing it to be green. But we're burning mostly hydrocarbons and hydrogen, other things in our fuel, but we're going to have CO2, N2O, SOx, NOx, unburned hydrocarbons, particulates. All these are coming from the combustion process, and we're going to discuss them in a little more detail. But some of them could lead to global warming, some to ozone layer depletion. Some might actually produce ozone. We'll discuss a little later why some's depleting it, when some's creating it, and why that's an issue. It's going to mix, create smog, and reduce our visibility. First, the smog. Okay, when the burners emit NOx, the NOx is going to react with ozone and VOCs in the atmosphere, reactive hydrocarbons, get their energy from the sun to complete the reaction, and it's going to create smog, which is a mixture of the words smoke and fog. Okay, some areas are prone to that. They don't have good wind to blow it away, or they have like a mountain range that will block the smog from leaving. So you have places like LA, Salt Lake City, where the mountains make a little bowl where the emissions can't escape, and you actually reduce your visibility. Not so much problem here in Oklahoma. Where are the other places that are listened to? Anybody remember? Looks like the one person showed up. Anyways, maybe they have smog there. All right. Any questions so far? Good. All right. Ozone. So ground level ozone is created when you have your NOx mixing with your VOCs, add your sunlight to give the energy of the reaction, creating ozone. And I passed out a flyer for you guys of the effects of ozone. Well, I'll have Chuck post it, Dr. Bokel post it on your guys' website or wherever he posts things so that other people can get it too. It's just something I found online from the government. Goes over some of the adverse health effects from ozone, whether it be for old people or young people or people that are very active during the day. But the ozone is highly reactive, and it will irritate your lungs, can cause problems with asthma, and if you already have chronic lung problems, it can worsen those. So ozone at the ground level is bad because it gets into our lungs and causes problems. But ozone up in the air, up in the high atmosphere, is good, right? It's what protects us from the solar radiation. Here's another showing of that, showing some of also where these emissions are coming from. So your VOCs, volatile organic compounds, you're going to get some from plants, trees, shrubs. But you also have some from industry and vehicles. We also need the NOx to mix with those. So where are we getting those from? Getting from industry, again, vehicles, and just a tiny sliver of that, natural resources. But as these combine together in the presence of the sunlight, the energy from the sun creates the ground level ozone. All right, up in the upper atmosphere. Again, this is blue and green and yellow, just so you know. The CFCs, have you guys heard of those? They used to be in like spray cans and things. Yep. It was found that those were depleting our ozone, our ozone. So those were rising up into the atmosphere, reacting with the sun, breaking down the ozone, and letting more radiation from the sun come in. They began noticing the hole over Antarctica, and it's growing, so they came together as countries. I think it was in Montreal Accord or something like that, and they were able to come to agreement that we needed to stop emitting CFCs, and as a result, been able to stem the hole in the ozone getting bigger, and it's actually expected to continue to recover. Okay, the Montreal Protocol. Now, we're going to get onto that pretty soon, but I don't want to spoil the surprise. It's coming up though, so hold on to your seats. Here's another view of it. This is a daily ozone layer. You can go online and look at these and see what the state the ozone layer is in. It's more exciting when it's in better color. Should I hold up my laptop in front of the camera? Probably not. All right. Acid rain. Okay. So when we have the sulfur and NOx entering the atmosphere, it has the opportunity to get entrained into the water cycle and mix with water from the air and form acids. Drop down as acid rain, which is damaging to the plants, damaging to things made out of limestone like cement. The cement will be dissolved by the acid and it'll be hazardous to our health. So this has decreased quite a bit over the last few years. Another cycle of this. So you have your sources, you have plants, you have natural sources. You know, in our original, earlier we had those little pie graphs showing that we do get some of these sources naturally. Comes up into the atmosphere, some mixes with the rain, falls down as wet acid rain, another can just be dry deposition. All right, here's the surprise, the greenhouse effect. So we talked about the Montreal Protocol, and now there's pushes, there's been meetings from several countries of the world to talk about greenhouse emissions. What we have going on is, as the CO2, which is being attributed as the main greenhouse contributor, is up in the atmosphere, the sun comes down, some of the energy from the sun gets reflected away, but other of it comes through to heat up the world, because we need the heat from the sun, we need the light. But then some of it, as it comes, it hits that CO2, and the CO2 changes it such in a way that when it goes to exit the atmosphere, it's different enough that it cannot go out. Kind of like in your car. You go in your car in the afternoon, it's really hot, hotter than outside, right? Because the sun is shining in, some of the light's getting absorbed by different materials in your car, different colors and such, and then it goes to exit, but now it's different and it can't get back through the windows and your car gets hotter. Here Dr. Buckle has a list of different greenhouse contributors, and they've set CO2 as a designation of 1 and then rated these other components at their effectiveness of at creating greenhouse contributions based off of that as the original. So you'll notice that methane creates 21 times more global warming potential. Nitrogen oxide, 310. You get some really big ones over on this side. Notice the CFCs, they've been phased out. But there's more than just CO2, right? In fact, water can also change it, but we need water in our atmosphere. Okay, so based on that list, you notice that CO2 is the main contributor. That's why it's the one that's focused on. Methane can be, you've probably heard on the news, it comes from cows chewing their cud, right? Or you have natural fizzers in the ocean where methane can be leaked out into the atmosphere, or drilling for oil. Okay, hopefully they have flares to burn that before it enters the atmosphere. Okay, here's breaking that CO2 into subgroups from the U.S. So down at the bottom, transportation. So your cars and trucks and trains, boats. Industrial, we're using that to, whether it be combustion or something. Residential combustion, commercial combustion, the territories. Got to have those in there. I don't know why they're separate, but they are. Electricity generation, and then all other sources. So a lot of these, transportation, you have internal combustion engines producing that. You have residential combustion and commercial combustion. Electricity generation, whether it's using a natural gas power plant or a coal-fired power plant. You have quite a few of that coming from combustion. Well then, why don't we do away with combustion, right? That'd solve the problem. But then we have to find a new way to replace combustion, right? But it's not that economical, okay? Well, we could shift, instead of us all driving internal combustion cars, let's drive electric cars. Well, then what is that just going to do? It's going to shift from the purple to the magenta. It's kind of close to this. This one's red and purple, but anyways, you're going to just shift where you're having that, right? Well, something to also consider would be efficiency. If we can increase the efficiency of any of these items, then it'll also decrease our footprint. You guys have any questions about greenhouse gases? I'm sure Chuck will come back, Dr. Bokel will come back to discuss that a little bit more next on Thursday. Here's another graphic of that. We have your virgin inputs, whether it's from being extracted from the earth, creating energy. If we're using it in some type of manner, whether we're combusting or manufacturing, okay, even landfilling is going to have emissions as those decompose, right? Have some aerobic organisms decomposing that, going to be emitting CO2. It comes over here, and we're going to have those emissions. Depending on what type of news you like to listen to, you could probably hear both sides of the story, right? So here's some data. Kind of, hopefully the data doesn't lie, but people can still skew data to how they want to. So just view things with your eyes open. You guys are learning a lot. It's a chance for you to understand what a problem is, what's contributing to the problem, what you think is not contributing to the problem, and use your knowledge to address that. You're the future. Mine's already 11 years past. Just some more graphs, data. Now notice these are up to 2000, so these don't have the last 19 years of data. So it can be changing. In fact, they don't really call it global warming anymore now, right? What do they call it? Good. All right. Might as well, right? Got the extra ones. Yep. So it used to be that everything was increasing, warming, and then now there's cooling change. So now we'll just call it climate change. Okay. Now, am I saying that CO2 is not causing a problem? No, I'm not saying that. Just saying that there's other sources of pollution. I was looking up volcanoes. Volcanoes produce a lot of CO2 when they erupt. Lots of SOx. But usually when they're not erupting, they're not producing as much. It's like 16% of the SOx emissions and like less than 1% of CO2 emissions when they're not erupting. Okay. Rising water. All part of the plan or not part of the plan? You can take your take on that. But there are ways to capture the carbon dioxide and make uses of it. I brought an example. I had to stop on the way here so I could bring you guys an example of capturing CO2 and using it for something good, right? We have carbonated drinks. They capture CO2 and they'll inject it into an oil well to help increase production from the oil. There's cryogenic purposes, I believe. But when you're forming all your products, depending on when you try to capture your CO2 would determine the quality of it and what you'll do with it as an end product. When I was in college, we had a letter come to our house. It went to everybody's house, it wasn't just us. But it said that your weeds cannot grow more than 1 foot tall. Okay. My definition of a weed may not be your definition of a weed. Right? Might look like a flower to me. To me, I see a beautiful pear tree, and if it has just flowers on it instead of actually producing pears, the one that flowers is a weed. The one that produces fruit, that's a good tree. So it's perspective, right? Some people see the CO2, and they're going to make money off of that. They can use that as a raw resource to be able to create value for something. So there's lots of ways to look at things. Come up with a way to use all that CO2 and you might be billionaires soon. Okay, so we've talked a little about CO2. The main goal of combustion is to take our hydrocarbon, mix it with the air and the heat, and result in CO2, not CO. Okay, CO2 is we finish the process. Along the way, we're going to have air that has 79% nitrogen in it going through our flame. It's going to create NOx. Dr. Bokel will talk about that Thursday. Hopefully none of the hydrocarbons are making it through the heater without being burned, combusted. Particulates, we're going to talk about those in more detail. The SOx. Basically, if there's sulfur in the fuel, it's going to be coming out the stack as SOx. Your PAHs and dioxins, we'll get to those as well. There's another one here hidden at the bottom. Did you guys see that one? Noise. It's not a problem I have. I tend to be quiet. I don't know if you guys can even hear me. But noise from combustion is actually an issue, especially when you're dealing with large flames like flares or some of the older style burners where it was a premix burner. That'd be a very intense combustion flame and create a lot of noise. So particulates are any solid matter that are in the flue gases. Reading in the chapter, it goes very well talks about that. There's 2 different types. In fact, I think we're going to talk about that in a couple slides. But it's going to be a coarse particulate and a fine particulate. Okay. Unburned hydrocarbons, just as it says, hydrocarbons that make it through the process without being burned, not mixing correctly with the O2. Carbon monoxide, when we have incomplete combustion. The NOx, I mentioned it mixes with the air, the nitrogen in the air. There's also fuel-bound NOx. So if there's any ammonia in your fuel or any nitrogens attached specifically to the fuel compound, then it's a lot easier to break that off than splitting up a double bonded nitrogen. Is it double or triple? Triple bond. There you go. Running out, guys. And these ones are my favorite. They're going to be harder to get away from. All right. Polycyclic aromatic hydrocarbons. Typically, we're not going to see those being present in the emissions from combustion processes in the heater. You might see those and also the dioxins. Those are going to be when you're burning something that would have those already present in them. So like when you're burning wastes in a thermal oxidizer. Okay. And we talked about the noise. You guys should ask Dr. Bokel about camels and noise. Okay? See what he tells you tomorrow, or Thursday. So to help reduce all of these emissions, to help improve the lives of people, we had the Clean Air Act passed in 1970. Formed up of several parts, but basically this is what's helped clean up our air. Okay? I guess I won't skip ahead. I'm going to tell you guys more about that in a little bit. how much that's helped. Another policy, though, that's helped is the cap and trade policy. So what the government does is they put a cap on how much individuals or companies can emit. All right? Now, the overall cap is set the same for everybody, but not everybody is going to use that cap. So they can have a trade established, okay, where they can trade their extras of their cap. And with this allowance that they're given, it's going to decrease over time to help incentivize them, but to give them time to reduce their emissions. Okay? And so you have 3 companies. Each one's given the same allowance, right? But each one actually uses a different amount. So company A, let's just call them Papa Bear. Papa Bear's doing good. You know, he's old, he's relaxed, he's got this much he can use, that's how much he's going to use. Okay? Mama Bear, she's a little more conservative, right? Don't want to take big risks, be a little bit more conservative, so she's only going to use part of her allowance. And then you have the kid, right? He's wild and crazy. He sees the future. He's going for it. See, he needs more than what his allowance is. What does Mama Bear do? Remember, she's not a risk taker. She sells him that extra allowance that she has, and now that allows him to run higher. But what happens in a few years? Each of these is going to get dropped, right? The allowance will be lower. Well, Mama Bear is going to be okay for now, right? Going to be equal. The boy or the child, it could be a girl, they had to go and completely redo their system. They had to implement a new technology. Now they're way down on their actual, on the, dropped it low. But Papa Bear, he was sleeping. Time's caught up with him, and now he's going to have to go buy from the child to get his back in order. So it helps, you know, bring it down in a time frame that they can handle, and allows for Mama Bear. She probably benefited well from being able to sell that off, increase her company. So there's 6 main criteria. Yeah.
So on that last slide, is there is there a minimum that the allowances are going to go? Because you're saying every year they're decreasing.
I bet the minimum they're shooting for is 0.
Yeah. So is there an expected time period when that's going to happen?
No. And governments, you know, they'll put out limits. Like, as an example, I was working on a project probably 8 years ago. Well, we were going to reduce the NOx emissions of some burners for a company in Chicago. And we're working on it. We did a bunch of modeling and all sorts of testing and stuff. And all of a sudden the project went away. And we called them, hey, what happened? Like, oh, we got an exemption on our permit for a couple more years. So, yeah. You never know. But yeah. Somebody's got to be pushing, somebody's got to be pulling, and then just moving along. Give and take till we get it all down to 0. It's a good question, but it's not worth 4 Reese's, sorry. Like I said, they're my favorites. It's got to be really good. But if nobody has one by the end, then it'll default to you. All right. So 6 criteria pollutants. These are ones that they're going to be measuring around your local area to see how your environment is following the EPA guidelines. Carbon monoxide, lead, nitrogen dioxide, particulate matter, ozone, and sulfur. Okay, I mentioned a little bit about the coarse and fine particles. Okay, how big's a micron? Anybody know? Pretty small. I'm going to have a picture of it on slide 37, so just wait. All right. So these have all been coming down with the EPA's Clean Air Act, okay? Cut CO2 almost in half, and this is as of 2002. So hopefully it's better now, even more. Drop NOx 17%, the VOCs in half, SO2 in half, and the PM10s by 30%. Check out lead, almost down to nothing, okay? I remember growing up, we had old man Murdoch. He had a big, huge farm. We'd always go play on it, and it had a big ravine in it. We called it the Gully. But one of the kids in the neighborhood ended up with lead poisoning. So everybody in the whole neighborhood had to go and get lead tested. So lead's not good. It'll give you poison. But luckily, we're emitting it. Remember, I don't know if you guys even have heard of leaded gasoline. Now, you see the signs that say unleaded? Well, it used to be regular, and then unleaded underneath that. But now regular is regular unleaded. Anyways, anybody had seen that before? Heard about it? You catch up. All right. Now I showed you that all that decrease, but if you look at, we're doing really well. If you look at our gross domestic product, that's increased 210%. Vehicle total miles traveled increased 170%. The population has steadily increased. Energy consumption is steadily kind of tapered off maybe a little bit. I'm sorry. It's increased a little. CO, it's the green one, but it's up here. Started tapering off. But look at those 6 ones that they're looking for. They've dropped by 71%, even increasing all of how much we're producing, how much we're traveling, just growth of our population. We're still bringing all those emissions down. It's much better than it used to be. Don't let them fool you. Though there's still room to get better. Here's some trouble spots. Doesn't quite show up as good as in the presentation here, but large population centers are going to have extra pollution. Okay. We have the mountains in here that's going to keep things trapped. The Appalachians run there. But the emissions, they are trending downward, even though we're producing more. Right. So here's a county by county NO2 emissions. So we didn't see that as a problem area on the last plot of the U.S., right? Even though there's quite a bit. Again, it's openness, right? There's room for things to dissipate. But this is all farm country, right? So what would be producing all those emissions? I can't hear you. You don't want to say it. All right. There's lots of tractors. Cows, right? Gotta end the cows. All right. So here's by source for NOx, transportation, fuel combustion. It's a bigger piece of the pie, right? So why are they going after the refineries? Well, it's easier to go after a big company than a bunch of people driving cars. Right? You said this is on YouTube, right? I didn't say that. All right. All right, I told you I was going to talk about the particulate matter, and I was going to show you a pretty picture. It's coming up. All right. So particulates, it's going to be solids, or in this case, liquid droplets. And there's going to be primary and secondary. The primary are going to be directly emitted into the atmosphere, and they're going to be coarse, they're going to be bigger. And then your secondary are going to be formed in the atmosphere, and they're going to be a lot finer. And the coarse ones are going to settle a lot easier, right? The little light ones are going to stay up there easier. As such, the smaller ones can travel further. So here's that description I was telling you about. This is a human hair. It's been blown up to show texture. But here you have 7 microns. I guess that'd be 70 microns because that's saying 10 microns for one section. So it's even smaller. Those are pretty small. So a PM10 is going to be particulates up to 10 microns. PM2.5 going to be up to 2.5 microns. So they're going to be the finer ones. If you have a emissions or pollution requirement based on that. Okay. It keeps going. Some of these problems with it can get trapped in your lungs, right? Those small molecules have a hard time getting out of your lungs. It can cause soiling and erosion damage and reduce the visibility as you get more and more of it. If you read in Dr. Bokel's book in here, he has a whole section on measurement of these particulates. There's the Bacharach method, the opacity method, and method 5, or ISO 9096. And this would be a specialty if you guys wanted to do that. Wouldn't expect a company to have an internal hire doing that. They would hire a company out based on the equipment needed and the expertise needed. That's what I would guess. We don't have a specialist that I know of. There's 800 people of us there. All right. Ozone. Back to ozone. You guys know a quick, easy way to find out if it's a good day or bad day for ozone? There's an app for that, right? If you guys look on your apps, like the Weather Channel app, click on that, and scroll down, or wherever, sideways, up, down, you can get to where it shows like your allergens and your UV, and one of those listed is ozone. Okay, so you guys can keep track of that. In Tulsa, we track the ozone days, right? They'll put them up on the signs, ozone alert days. What are some of the things they ask you not to do on an ozone alert day? Or to do? They want you to carpool, don't fill up your gas tank, don't mow your lawn, right? So driving around a lot, you're going to be creating more emissions, filling up your gas tank, probably letting off VOCs as you're doing that, the fumes. Right, so to help decrease the overall amount in the air. That's why they're asking us to do that. But we've been doing a lot better. We haven't had as many ozone alert days the last few years. Okay. What time does this class go to?
45.
1:45. It's a good thing I put a lot of homework problems at the end. All right. Air toxics. So hazardous air pollutants, HAPs. There's 188 that are suspected to cause or known to cause cancer or other serious health effects. And some examples of those are benzene, chlorochloroethylene from dry cleaning facilities, methylene chloride, paint stripper, and dioxin, asbestos, toluene, mercury. Right. And as I mentioned before, these aren't going to be derived from breaking up methane to combust it. These are going to be items that are either being burned in the flame as a separate source put in the flame, or it'd be contaminants that are actually bound to the fuel. All right. Okay, the last topic in the presentation before we get to the homework section is general control strategies. How can we control our emissions? All right, so we have a system shown on here. We have the fuel and oxidizer, most times is air, going through the burner. Probably has a little copper in their fuel making the green flame. And it's going to come out as your flue gases. You'll have, here's showing the load. Typically that would be inside the heater. It's more efficient that way. All right. What we're going to do to control the emissions is we're going to separate this into sections. The first section, pre-treatment, right? So say we know that there's sulfur in the fuel, right? We don't want to have to get it out of our flue gas, so we're going to treat our fuel to get the sulfur out, okay? We could also, depending on the full setup and the efficiencies of our system, we might be able to preheat our fuel so that we don't have to burn as much because we're being more efficient on our whole process. Let's go back actually. Another way is, I mentioned that it's usually air as our oxidizer. What if we don't use air? What if we use pure oxygen? All right, does that sound hot? Whew. It is, right? If we put in pure oxygen, then we don't have to heat up all that nitrogen. But if we're not heating up nitrogen, there's no nitrogen present, we're not going to be creating any NOx. All right, so that would be another way to do it. And then to get away from the super high temperatures of burning with pure oxygen, what you do is you'd recirculate your flue gas into your system to cool the flame down. Okay, maybe we'll heat up our load. Maybe we'll have a preheater on our convection section that's going to heat up our crude oil so that we don't have to burn as much inside the heater. Another way that we could reduce. Combustion modification, right? There's different types of burners that are going to create different amounts of NOx. So we might need to change the burner, change the way the burner's set up. I mentioned that preheating our oxidizer, our fuel, could help increase the efficiency. It does have a slight penalty on your NOx, though, when you do that. Chuck will talk to you about that on Thursday. I'm sorry, Dr. Bolkel. Sorry, Chuck. Does he watch these? Well, if he does. All right. There's also recirculation that we can do in the furnace to help reduce the NOx. You can actually pull flue gases out and pump them into the burner to help cool the flame. You know, it's only 900 degrees. That's nothing for a 2300 degree flame, right? Hot to us, cool to the flame. So we're going to cool that down, change our emissions. Process modification. Is there a different way to heat the process? Is there a catalyst that can be used so we don't have to use such high temperatures? Okay, can change the process. An example that Dr. Bokel has used a lot is he was working at a glass plant. I don't know if he told you that, but he'd constantly hear breaking glass, right? They're having impurities in their glass, so they'd have to break it, send it back, start over. If they can modify their process so that they don't have all those impurities, they just run it through one time, much more efficient, and you're decreasing your emissions. And post-treatment. You guys got that lecture last time, right? Post-treatment, whether you're using an SCR or NSCR. For SOx, you have scrubbers, different methods for reducing, getting those emissions out of your flue gases. Okay. In summary, for the homework, don't get your stuff yet. We'll do our homework now, right? You laugh? Well, based on our interaction, you think it's going to be long? Numerous potential problems associated with combustion emissions. The cap and trade, the Clean Air Act, all used by the government to help get that in check, right? If we just let capitalism, you know, to some it's a bad word, run rampant, maybe we wouldn't be where we're at today with our clean air. So it's good to have a checks and balances system. And, you know, coming from a burner manufacturer, without those, we probably wouldn't be making such great equipment nowadays and developing more for the future. Okay. Those 4 general strategies for minimizing the emissions: pre-treatment, change your process, improve it, efficiencies, change your combustion, and post-treatment as well. All right, to give credit where credit's due, got information from the EPA and the IPCC, and of course, Dr. Bokel's book. Back to our pollution problems. All right, fun part. Should we have it be a pop quiz? You guys didn't read the chapter, so I need to get you with something. We have a heater, and it's emitting 25 ppm of CO, 40 ppm NOx, 4.5% O2 at 600 degrees. So that's leaving the stack at 600 degrees. The temperature inside the heater is 1500 degrees. Our state permit allows for 30 ppm CO and 50 ppm NOx at 0% O2 basis. Are we within the permitted emissions? Oh yeah, of course, look. 25, and we were allowed 30, 40, we're allowed 50. Piece of cake, right? We done? So there used to be a phrase, the solution to pollution is dilution. Not the case, okay? If you just pump in a bunch of air, then you decrease your ppms because you're not changing the mass of your NOx or your CO. You're just diluting it. So to keep everybody on level ground there, we have to correct for that 4.5% extra O2 in the air, or sorry, the flue gas. So, and if not, is the burner operating as guaranteed? First of all, in chapter 14, Chuck has some equations already listed out for you for converting that to 0% O2. Do you guys already know that equation? Since you guys don't have your books, what you do is you take your raw value, how much you measure, and then you use this equation here to change that. You have 20.9 minus 0, so that's your reference point. That's what we need. We need to be at 0%, and then 20.9 minus 4.5, which is your measured. Again, that's equation 14.1 in the book. Okay. And the answer is 19.1. All right, so we are good on that one. We are under the permitted value. Check. Let's check the NOx. I'm going to use the same formula. So in this case, 40 ppm NOx measured. Again, 20.9 minus our reference of 0. 20.9 minus 4.5, which was what we measured. And the magical answer is 51. We're over our permitted value. All right. So notice that as we take that dilution out, that our emissions are going, the actual emission is higher. So now to know if the burner is operating as guaranteed, because they're going to be calling me saying, hey man, we're over our guarantee here. We have to find out what the burner was guaranteed for. So in this case, the burners were guaranteed to not exceed 25 ppm CO and 20 or 40 ppm NOx at 3% excess air, volume dry, at 1400 degrees F for the maximum and normal duty. Okay. So the burner is going to be designed for a minimum, normal, and maximum. And when we design the burner, we're going to optimize it for maximum and normal, because that's where it's going to run 99% of the time. Now, in some cases, in some states, they're increasing their emission requirements, and they do, in fact, now require guarantees at minimum heat releases, which is a challenge, but that it drives innovation, right? So anybody already started the calculations? Now we're going to use equation 14.3 on page 385. And we're going to add a correction for the temperature. All right. So we have 40 ppm NOx raw that we measured. We're going to correct it. 20.9. There's an error right there. That's sad. We'll correct it live. All right. Our reference is 3, and our measured is 4.5. Okay. Who's got? I was playing with it. But I'm not done. It's going to do it again. All right. Back online. Has somebody run through this calculation yet? All right. Then this 1400 is our reference minus 400. So this temperature correction is based on empirical. If you probably noticed 20.9, wow, that kind of correlates with the amount of oxygen in air, right? But this 1400, that's empirically been determined with 50, 60 plus years of burner testing. Okay, so you're going to take your reference minus 400 divided by your measured. No, that was right. Reference, and your measured is going to be on the bottom. What's the value on that? 39 point. Whoa. $39.7. Well, that's no good because now. Oh wait. Well, let's go back. We're guaranteed not to go over 40. So it's right on the edge. I'd get to go home and sleep well that night. All right. But color. We got to go back. We got to start over. Look, smiley faces are it's the right color. All right. So you're gonna, if you're at your company, you come to us and say, well, my burner is over the emissions, and I say, yeah, but it's under your guarantee. Well, what do I do? Tune in Thursday. Chuck's gonna help you with that. Okay. Well, I want to go back. I want you guys to see that we don't have a green sun.
Look at all the colors. Told you you're confused. Don't trust the engineer.
Oh, this one's pretty too. See that? Ah. Aha. See? Now we can all feel better that knowing outside it has a yellow sun. All right. Does anybody have any questions? All right. I don't know his name, but he won the Reese's bar.
Sweet. Thank you.
Woo, that was quick.
I could have got it if I wanted.
All right.